Welcome. We have been discussing the Hodgkin-Huxley equations and phase plane analysis, and with that we discussed how action potentials show all or none behavior, or how the Hodgkin-Huxley system of equations have what we call a true threshold. We also discussed how to find in the phase plane whether limit cycle exists in the system or not, or whether the system can go into oscillations or not. And basically those two are very important features of nonlinear systems and plays an important role in defining action potentials, and in fact saying that they are all or none events. And similarly, oscillations, we will see, also play an important role in many other factors when we discuss more of the network level phenomena to understand the behavior of neural systems. Now, among other things, some of the important things that Hodgkin-Huxley equations allowed us to show, as mentioned last time, is anode break excitation. Or we will call it in short ABE. And the other we mentioned is the relative refractory phenomena. So, what are these things? So, anode break excitation, as the name suggests, is that if we, first these were experimentally observed, and then the Hodgkin-Huxley equations actually were able to explain this behavior. So, if we inject a negative current, that is, if we hyperpolarize a neuron for a relatively long period of time, few hundred milliseconds, with maybe even a small current, for the Hodgkin-Huxley equations about a 3 microamp per centimeter square current is sufficient to show that. So, then if we release the negative current or stop the negative current, following that stopping, there is a excitation that causes action potentials at the end or after the end of the hyperpolarizing current. So, here is how it would look like. Let us say this axis is the current and this axis is time, and so if, let us say, this is 0 current and we have a current clamp that would look somewhat like this, that is, we are injecting a negative current, let us say minus 3 microamp per centimeter square, and we are measuring the, and so at this point, which is a few hundred milliseconds later, we are stopping the negative current and making it 0. So, we have a current clamp of minus 3 microamp for the this intervening period, and then we come back to the 0 current level. The corresponding voltage that we are measuring, so at the 0 current level, it is supposed to be at V rest. This is the voltage now, and because of the negative current, we are basically injecting negative ions effectively into the neuron. There will be a hyperpolarization as expected. Hyperpolarization meaning that the voltage will go down and basically stabilize to some negative value for that particular current, and it will stay on like that up to the point of release of the current clamp, of the negative current clamp. Now, after this, because that negative current is gone, obviously the system will again try to go back to its resting state. So, this is our V rest level as on the left hand side. So, this will try to go back into the resting state and try to stay on to the V rest. So this is not exactly what happens, and will show in the model, in the Hodgkin-Huxley model, as well as experimental data shows that here it actually overshoots beyond the V rest, and there is an action potential produced, and then it goes to V rest. So this phenomena is the anode break excitation, or ABE. That is, when we release a neuron from hyperpolarization for if it is there for a long period of time, then it produces an action potential at the end. So to understand why this happens, we can think about the Hodgkin-Huxley equations and what happens to the different gating variables at this particular region of time. So as we know, let us say we have our, let's say this is V and M infinity curve, M infinity as a function of voltage. Let us say this is our V rest equals minus 60 millivolts. We know that our M infinity goes like this and reaches about 1. Then if we draw the N infinity V on top of it, it is somewhat like this, with a higher value at V rest around 0.3, and now the inactivation gates whose gating variable is H, they at V rest remain at around 0.6 and then go down, back down to 0. So this is H infinity V. So this value here is about 0.6. So when the neuron is at rest, our M values are very small. This is about 0.1 or so, or even less. Our N values are around 0.3 here, and H is around 0.6. So with these values of M, N and H, which essentially implies certain probability of sodium channels and potassium channels being open, these values provide the equilibrium condition where the net current is 0. That is, the I sodium, I K and I leak together sum to 0. So remember that is the V resting, and any fluctuations from here would try to would be not at equilibrium. So they may go on to they may produce different phenomena. So what we also know is, if you recollect, we have M is very fast, and as we did for the VM system to understand threshold behavior, we take N and H at the value what they were when we initialize the system, when we considered the VM system. And in the VM system we can understand threshold phenomena because the model is valid only for the beginning few milliseconds. So in this case we keep again N and H, we can consider N and H to be fixed to the initial value, but now instead of at V rest, we will now consider the situation in this particular scenario, that is when the current clamp is being ended, that is shown with the green line. So we have all the M, N and H gates held at some lower value than V rest. So, at this particular time, our H value is H infinity VR minus whatever this value is, let us say delta. So, here if we consider the curve, we have moved the system down to VR minus delta. And so, here at the same point, n is at n infinity VR minus delta, that is the steady state value of H and n at that particular voltage. Since we are holding it for a long period of time, we can say that they have reached there, H has reached its steady state value and n has reached its steady state value, and obviously m is very fast, it must be at its steady state value, that is m infinity VR minus delta. So, what are those values? At this point, we have a situation something like this, where my m infinity V is hardly changing, because there is a small change in the m infinity values with that delta change, because initially itself our sodium activation gates opening probability is very low. However, there is a larger change in terms of the values of n and in terms of the values of h. So, this turns out to be around 0.7 and this turns out to be around 0.23. So, now if we consider the, so think of the system now, we have H, N and M at these particular values, the voltage has shifted to VR minus delta and we suddenly remove that I external. So, the system will now try to go in the direction that the net current will drive it towards, and that is it will try to go towards V R, and in doing so, if you think about it, m infinity is very fast, and so the voltage can be increased by the sodium channels activation gates. We have H as high, H is high here and N is low, and these can be considered as fixed to the values we are starting the system with at the end of the current clamp. So, H is very slow, it stays at H infinity VR minus delta, that is, it is going to change very slowly. So, by the time m infinity has gone to m infinity V from m infinity VR minus delta, that is, it has changed to m infinity V, by this time it has changed to m infinity V, H is still at H infinity VR minus delta effectively, and N is still at N infinity VR minus delta because of their long time constants or large time constants. So, now what happens is that our V has reached, so this is VR, V has reached VR. So, let us consider it here, V has reached VR. So, that is the resting membrane potential. We know that at this stage the system is in equilibrium, or the net current is 0 only if our H is at H infinity VR and N is at N infinity VR and V is at V infinity, M is at M infinity VR. However, we do not have that. H is larger than the resting membrane resting value and N is lower than the resting value. So, we have a net current that is not 0. remember, as we said, at the V rest the net current should be 0. But in this scenario, although the voltage reaches VR, in this particular point voltage has reached VR, but the corresponding values for H and N required for the neuron to have no net current and be at VR, we do not have that, and H is larger than that, N is smaller than that, and H being larger than that means that more sodium current will be flowing in as expected from its gradient. So, sodium conductance is proportional to m cube H, of which this H has increased. So, 0.59 to 0.7. So, 0.7 to 0.6. So, that means that more sodium channels are open at this point, which means that there will be sodium influx trying to make the membrane potential go towards E sodium, as we know. Similarly, N, which is the potassium activation gate, is lower. That is, our N to the power 4 has decreased, and now the role of N is to make the potassium ions go out. And so, at equilibrium or at V rest, the number of potassium channels available to remove from the inside is getting lowered in comparatively in this case, because N is lower. So, the potassium ions which would naturally supposed to be outside are now inside and do not have that much conductance to flow out. And this is basically effectively another positive additional net positive current into the neuron. These two currents together, this net balance current left when the membrane potential is at V rest, but H and N are not at the steady state value for V rest, we get keep on increasing the membrane potential, and the same phenomena that we observe during action potential generation, that same thing is repeated and we get an action potential. So, this phenomena is explained by the Hodgkin-Huxley equation. So, in the code provided for Hodgkin-Huxley equations, you can run this and see for yourself that this is what the model shows, and this is also what was observed in real neurons, and this was the first time it was explained by Hodgkin and Huxley how anode break excitation happens. So, to look at it in more details, so this was less quantitative in the sense that it was a qualitative description, but we can have a quantitative description in the sense of using our numerical simulation methods and using phase plane analysis. So, let us say we have this as V, and we are considering another state variable. In this case it is M. So, since we are looking at threshold crossing phenomena, again we will have M as our other state variable, and as discussed in the previous slide, we are keeping H as fixed to H infinity V minus VR minus delta, and N is fixed at N infinity VR minus delta, which is their steady state value at the end of the current clamp. So, we have our C dV dt equation and our dm dt equation. These two will define our system's behavior, at least in the initial few milliseconds, which will show us the anode break phenomena. So, here we have I external. Remember, this I external is now 0 when the clamp is released, and minus we have our G sodium bar m cube H infinity VR minus delta minus GK bar n to the power 4, the value at VR minus delta minus G leak and V minus E leak. I am sorry, we have one more term here, that is, this is N at this, and then we have V minus EK. Let me erase this fully. So we have V minus EK. So remember that this is N as a function of, or a function of VR minus delta, in the sense that this is a constant, and to the power 4. Similarly, this is also a constant, not VR minus delta is not being multiplied. We will have here I'm sorry, let me just erase this and rewrite this. So we have m cube H infinity VR minus delta times V minus ENA, I missed these, minus GK bar n at n infinity at VR minus delta to the power 4 times V minus EK minus G leak V minus E leak. So now from this we can get the dm dt equals 0, that is the m null line, which is the same as what we have seen before, which is, it is going to be something like this, just the same curve, or the m infinity curve as a function of voltage of, sorry, but we are actually plotting the m value here, and this curve is like the m infinity curve. Similarly, we can have the dv dt equals 0 set out as m as a function of m and v equation, which we had earlier shown to look somewhat like this, where we have two particular nodes here. So this one is the resting membrane potential, which is our VR, which is around minus 60 millivolts. This is a saddle node, and this is again a stable node. So this is a saddle, this is again a stable node. So this resting membrane potential, point is also a stable node, and we have a stable manifold coming in to this particular saddle node, which is what is providing us the threshold phenomena. That is, if we start with a voltage somewhere along this line, then beyond this point where we get threshold. So now the same thing is the same phase plane can be plotted with these values of H and N. So this was plotted with H infinity VR as H and N infinity VR as the N value. When we change this to VR minus delta, the phase plane, the null lines will change. As you can see, if we change this, the dm dt or equal to 0, which is the m null line, is not going to change. However, because of the change in H infinity and N infinity, the dV/dt nullcline is going to change. And what happens in this case is that we are now starting the system also at a slightly lower value of m from 0.1 and a Vr minus delta somewhere here. We are starting the system somewhere at this point. This is where the system is, the green dot, at the end of the current clamp, which we had shown by the circle at the end of the current clamp in green. And now the dV/dt nullcline, which is this one, dV/dt equals 0 or V nullcline, that changes to a different shape moving vertically downwards and becoming like this. So now what happens is that there are no equilibrium points in this region. The two equilibrium points, one that was the initial stable node, which was the resting membrane potential, and the saddle node, which provided the threshold because of the stable manifold, those two nodes are gone. Those two equilibrium points are not there anymore. And we have the system starting at that green dot. So what happens is that the system follows along this route and goes up to this particular stable node, because that is the only stable node present and the direction of flow will take it onto there. And that is essentially that the m has reached up to +1, which is basically the upstroke of the action potential that we are seeing here. The action potential, the complete action potential obviously cannot be shown here, because we again need the changes in N and H to be incorporated to bring back the membrane potential down. But we are showing that indeed it is the voltage is going towards the making the upstroke of the action potential, which is sufficient in this case with the Vm reduced system. So we have qualitatively explained the anode break excitation with the help of the Hodgkin-Huxley system of equations. We model the anode break excitation with the Hodgkin-Huxley system of equations, and with the phase plane analysis with a Vm reduced system, we can show the anode break excitation and the reason behind anode break excitation. So next, in our next lecture, we will consider the issue of refractory or relative refractory following the spike, which is also an important phenomena that can be shown by or understood by the Hodgkin-Huxley equations. Thank you.